5 minutes ago, in observatories scattered across the planet, scientists were staring at new images of an object that came from outside our solar system entirely, moving too fast, shaped too strangely, and behaving in ways that one of Harvard's own astronomers says might not be natural at all. The James Webb Space Telescope has now captured its clearest look yet at 3I Atlas, and depending on who you ask, what it shows is either a completely ordinary comet or something a lot harder to explain. Stick around, because this is one of those rare stories where actual working scientists are publicly disagreeing with each other in real time, using real data, real telescopes, and real published papers, not internet speculation. By the end of this video, you will understand exactly what Webb found, why one prominent physicist keeps calling it anomalous, and why the vast majority of the scientific community still thinks the explanation is far less exciting and far more fascinating than an alien spacecraft. This is a story with no clean, tidy ending yet, and that is exactly what makes it worth understanding properly, instead of settling for whichever version of it sounds most dramatic in a headline. Let's start with the basics, because 3I Atlas is already a big deal even before you get to any of the controversy. It was first spotted on July 1st of 2025 by the NASA-funded Atlas Survey Telescope in Chile. And the moment astronomers calculated its trajectory, they realized it was not orbiting our sun the way every planet, asteroid, and regular comet does. It was moving on a hyperbolic path, meaning it came from interstellar space, passed through our solar system once, and is now on its way back out, never to return. This makes 3I Atlas only the third confirmed interstellar object ever detected passing through our solar system, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Every single one of these objects is essentially a visitor from another star system entirely, a physical piece of some other solar neighborhood that happened to drift close enough for our telescopes to catch it before it disappears again forever. It helps to remember just how much controversy the first of these visitors, Oumuamua, already generated years before 3I Atlas ever showed up. Oumuamua was small, oddly elongated, and appeared to accelerate slightly as it left the solar system without showing any of the visible gas or dust tail astronomers normally expect from an outgassing comet. That mismatch was exactly what first led Avi Loeb to publicly propose, back in 2017 and 2018, that Oumuamua might have been an artificial object, possibly even a thin, lightweight solar sail reflecting sunlight in a way that could explain its unusual acceleration without any visible cometary activity. That earlier debate never reached a fully settled conclusion, since Oumuamua left the solar system before scientists could gather enough additional data to rule definitively one way or the other, and it set the stage for exactly the kind of heightened attention 3I Atlas is now receiving from the moment it was discovered. Borisov, the second interstellar visitor, behaved much more like an ordinary comet from the start, complete with a visible tail and chemistry that closely resembled comets native to our own solar system, which meant it attracted comparatively little of this kind of speculation. Multiple space agencies immediately mobilized to study it using every instrument available. NASA's Hubble Space Telescope, the James Webb Space Telescope, the Sphere-X Observatory, the TESS exoplanet hunting satellite, and even spacecraft that happened to be in the right part of the solar system already, including the Lucy mission on its way to the Jupiter Trojan asteroids and the European JWST spacecraft, all turned their instruments toward this fast-moving visitor. Even NASA's Mars, orbiting MAVEN spacecraft, and the Punch mission, originally designed to study the sun's outer atmosphere, ended up contributing observations, giving researchers an unusually complete, multi-angle picture of the same object, gathered almost simultaneously from across the solar system. That is an extraordinary amount of scientific attention for a single object, and it tells you just how rare and valuable this kind of visitor actually is. Interstellar objects like this do not orbit our sun and wait patiently for us to study them at our leisure. They pass through once, and once they are gone, that specific window of observation closes forever. In August of 2025, the James Webb Space Telescope used its near-infrared spectrograph instrument to take its first detailed look at 3I Atlas, and by December, after the comet had swung around the sun and begun heading back out of the solar system, Webb used a different instrument, the mid-infrared instrument, to capture what scientists call its first chemical fingerprint of an interstellar object. This is not a photograph in the way you might picture a photograph. Instead, Webb splits the light coming from the comet into its component wavelengths, allowing scientists to identify the exact molecules present based on which specific colors of infrared light are being absorbed or released. Every chemical element and compound absorbs and emits light at its own distinct, predictable set of wavelengths, almost like a barcode unique to that substance. And by carefully measuring which of these barcodes show up in the light coming from 3I Atlas, Researchers can identify precisely which molecules are present-T in the comet's surrounding cloud of gas and dust without ever needing to physically touch, or sample the object itself. The results were genuinely remarkable. Webb detected water vapor, carbon dioxide, carbon monoxide, carbonyl sulfide, and notably methane, escaping from the comet's nucleus, with water vapor spreading out much farther into the surrounding coma, while the carbon dioxide and methane stayed concentrated closer to the object's core. This layered structure, water spread wide, while carbon dioxide and methane cluster, tightly near the nucleus, actually tells scientists something useful about how the comet is physically built. Water ice typically requires a bit more warmth to sublimate directly off the nucleus itself. So much of the water vapor detected around 3I Atlas likely comes from smaller icy grains that have already drifted away from the nucleus into the surrounding coma before evaporating there instead. Carbon dioxide and methane on the other hand, sublimate at much colder temperatures, meaning they can escape directly from the nucleus itself even while the object is still relatively far from the sun's warmth, which is exactly why Webb found them concentrated so much closer to the object's icy heart. Reading a comet's chemistry this carefully, essentially reconstructing its internal structure from a distance using nothing but the specific wavelengths of light it gives off, is precisely the kind of measurement that was simply impossible before instruments as sensitive as Webb's existed. Here is where the story starts splitting into two very different narratives. On one side, you have the very real, very well-documented data. 3I Atlas turned out to be significantly larger and more massive than either of the two previous interstellar visitors, with some estimates suggesting a nucleus potentially exceeding 5 kilometers in diameter and mass estimates running into the tens of billions of tons, dramatically bigger than the relatively small, elongated shape of Oumuamua that sparked so much speculation back in 2017. To put that size difference in perspective, some researchers have estimated the nucleus of 3I Atlas could be roughly 1,000,000 times more massive than Oumuamua and 1,000 times more massive than Borisov, an enormous jump across just 3 known examples of interstellar visitors, and one that naturally raises the question of whether we happen to get extraordinarily lucky detecting an object this large so soon, or whether interstellar objects this size are simply far more common throughout the galaxy than astronomers previously assumed. Researchers also found something scientifically puzzling: a higher than expected ratio of nickel relative to iron in the comet's chemical composition, along with a notable absence of the kind of dramatic, easily measurable, non-gravitational acceleration that classic comet outgassing typically produces. When a comet sheds gas and dust, as it warms near the sun, that outgassing acts a little like a tiny, uneven rocket thruster, nudging the object's trajectory slightly off a pure gravity-only path. Careful tracking, using thousands of observations from more than 200 observatories worldwide, found this effect was smaller than expected, given how much material the comet appeared to be losing. Specifically, one analysis using data gathered between May and September of 2025 found the object's actual measured position stayed remarkably close to a pure gravity-based trajectory, with residual deviations small enough to place a strict upper limit on how much non-gravitational acceleration could possibly be present, a limit researchers used to argue the nucleus must be unusually massive and large in order to resist being pushed off course by its own visible outgassing. Then, closer to perihelion, the comet's closest approach to the sun, a different pattern emerged. Multiple tracking teams detected a measurable non-gravitational acceleration after all, one that, according to Loeb's calculations, would require the comet to have lost roughly 10% of its total mass through outgassing alone in order to produce that specific amount of extra push. That is an enormous amount of material to shed in a relatively short window, and it raised an obvious follow-up question. If the comet genuinely lost that much mass, there should be a correspondingly massive, dense cloud of gas and dust visible around it in the weeks that followed, observable by instruments like the European JWST spacecraft or ground-based telescopes back on Earth. Enter Avi Loeb, a Harvard astrophysicist and director of the university's Institute for Theory and Computation, who has built a public reputation over the past several years for proposing that unusual interstellar objects might be artificial rather than natural. Loeb has published an extensive, continuously updated list of what he calls anomalies surrounding 3I Atlas, ranked roughly by how confident he is that each one lacks a simple, natural explanation. He has pointed to the object's unusually precise, low-tilt trajectory through the solar system, its immense size compared to previous interstellar visitors, its unexpected nickel-to-iron ratio, and perhaps, most dramatically, a coincidence involving the comet's closest approach to Jupiter. According to Loeb's calculations, 3I Atlas is projected to pass extremely close to Jupiter's Hill radius, the specific boundary where Jupiter's gravity becomes stronger than the Sun's. A distance he calculates matches almost exactly differing by a probability he describes as roughly 4 in 100,000 of happening by pure chance. Loeb has openly speculated that this could indicate an intentional maneuver, potentially even the deployment of smaller technological objects at gravitationally stable points near Jupiter, though he is careful to frame this as one possible interpretation among others rather than a settled conclusion. Loeb has also pointed to the timing of the comet's arrival through the solar system as another item on his list, noting that its trajectory brought it within tens of millions of kilometers of Mars, Venus, and Jupiter, while conveniently remaining largely unobservable from Earth's own vantage point during its closest approach to the Sun, a coincidence he argues is worth flagging even if it does not, on its own, prove anything unusual. He has been careful throughout his public writing to present these observations as a ranked list of open questions rather than a single unified conclusion, repeatedly noting that scientific truth should be determined by data rather than by consensus or authority, and stating plainly that he expects to know more as additional observations continue rolling in over the following months. While we are digging into a genuine scientific controversy playing out between real astronomers instead of manufactured drama, if that kind of grounded, source-based approach to space news is what you come to this channel for, go ahead and hit that like button and subscribe if you have not already, because the pushback against this theory is just as important as the theory itself, and there is substantial pushback coming from a large portion of the astronomical community. Other researchers analyzing the exact same trajectory data have pointed out that the precision of 3I Atlas's measured position is inherently limited by the fact that comets are fuzzy, diffuse objects surrounded by gas and dust, making it genuinely difficult to pin down an exact center of mass with the kind of pinpoint accuracy Loeb's calculations rely on. Independent teams of astronomers have published their own competing analyses of the same non-gravitational acceleration data, and multiple groups have concluded that a relatively modest, kilometer-sized icy nucleus undergoing completely ordinary cometary outgassing adequately explains the observed acceleration without requiring any exotic explanation at all. One team, using models of water and carbon dioxide sublimation rates, calculated a nucleus radius of roughly 400 meters, far smaller than the multi-kilometer estimates Loeb's earlier calculations implied, illustrating just how sensitive these size estimates are to the specific assumptions each research group builds into their models. Another independent analysis, using a different mass loss model entirely, arrived at a diameter estimate in a broadly similar range between about 800 and just over 1,000 meters, reinforcing the idea that ordinary cometary physics can plausibly account for the observed motion without needing anything unusual at all. One widely cited rebuttal specifically noted that the statistical uncertainty in measuring such a faint, distant object's precise motion is large enough that many planetary scientists remain skeptical of the very anomaly Loeb's argument depends on in the first place. Critics have also raised a more general methodological concern about how anomaly-based arguments tend to work in practice. When you compile a long enough list of individually unlikely seeming coincidences, statisticians point out that some of them will inevitably turn up by chance alone, simply because so many different measurements and comparisons are being made across such a large, complex data set. A single planetary scientist reviewing Loeb's list publicly noted that the underlying uncertainty in measuring a faint, fuzzy object's precise trajectory this far from Earth is large enough that much of the apparent anomaly may simply reflect the limits of current measurement precision rather than any genuinely unexplained physical behavior. As for the nickel-to-iron ratio that raised eyebrows, researchers studying comet chemistry have pointed out that unusual metal ratios have actually been observed in other solar system comets before, tied to how certain compounds sublimate at different temperatures and rates as a comet warms near the sun, rather than requiring any artificial explanation. And regarding the dramatic Jupiter Hill radius coincidence, several astronomers have noted that predicting a precise future close approach this far in advance carries its own significant uncertainty, and that apparent numerical coincidences, however striking they look laid out in a headline, are a well-known hazard in orbital mechanics, where thousands of possible near misses and close approaches exist across the solar system, making an occasional close numerical match statistically much less surprising than it first appears. This is really the heart of how legitimate scientific disagreement is supposed to work. And it is worth sitting with for a moment because it looks nothing like the manufactured screaming conflict internet content usually implies. Nobody involved in this debate is hiding data. Loeb publishes his calculations openly, in detail, with the underlying numbers and methodology available for anyone else to check and challenge. His critics respond the same way, publishing competing analyses using the same publicly available observations, showing their work, and explaining specifically where. They believe the original calculations went wrong or relied on overly optimistic precision. That back and forth, uncomfortable and occasionally public as it gets, is exactly the process that eventually settles genuinely uncertain scientific questions, even when it takes years and even when one side is a minority voice pushing against the mainstream consensus. What makes 3i Atlas worth paying attention to regardless of which explanation eventually wins out is what Webb's data revealed about where this object actually came from. In June of 2026, a team of researchers published a paper in the journal Nature analyzing the precise ratio of deuterium, sometimes called heavy hydrogen, to ordinary hydrogen found within the comet's water. This ratio acts almost like an isotopic fingerprint, offering clues about the specific conditions under which the object's ice originally formed, potentially billions of years ago, around a star system entirely different from our own. Scientists have spent decades measuring the same deuterium to hydrogen ratio in comets native to our own solar system, building up a well-established baseline for what typical solar system ice looks like at this specific chemical level, precisely because that ratio tends to get locked in place at the moment. Ice first crystallizes and rarely changes much afterward, even across billions of years of drifting through space. The results genuinely surprised the research team, since the specific chemical signature did not cleanly match patterns seen in solar system comets, suggesting 3i Atlas formed under conditions astronomers are still working to fully understand in an environment unlike anything sitting in our own cosmic backyard. Think about the scale of what that actually means, independent of any alien spacecraft debate at all. This is a physical chunk of material, ice, dust, and organic molecules, that condensed around a star system light years away, survived an unimaginably long journey through the emptiness of interstellar space, and happened to drift close enough to our own solar system for humanity's most advanced telescopes to study it in detail before it disappears again forever. This time, genuinely forever, since 3i Atlas will never pass this way again. Even in the most boring, mundane, purely natural explanation, that is still one of the most remarkable scientific opportunities of the decade. A direct physical sample from another corner of the galaxy passing directly through humanity's collective backyard. So where does that leave the actual question this video started with? The honest answer, the one that respects both the excitement and the uncertainty, is that the vast majority of professional astronomers studying 3i Atlas currently favor the explanation that it is an unusually large, unusually composed, but ultimately natural interstellar comet, one whose specific size and chemistry happen to produce some genuinely puzzling measurements that require further study to fully explain. Avi Loeb's technological artifact hypothesis remains a minority position within the field, openly published and rigorously argued, but currently unsupported by the weight of independent analysis from other research teams working the same numbers. Loeb himself has repeatedly emphasized that he is not claiming certainty, only that the data deserves rigorous testing rather than automatic dismissal, and that upcoming observations, particularly any evidence of unexpected maneuvering near Jupiter, would represent what he calls a genuine acid test for the more exotic hypothesis. Either way, the story is not over yet. 3i Atlas is still being tracked by observatories around the world as it continues its one-way journey back out of our solar system, and every additional data point either strengthens the mainstream cometary explanation or adds one more entry to Loeb's growing list of anomalies. Loeb himself has pointed to the object's projected close approach to Jupiter in March of this year as a genuine test of his hypothesis, one he describes as an acid test capable of producing a clear result either way. If the object continues drifting along an entirely predictable, gravity-dominated path with no unexpected maneuvering, that outcome would weigh heavily against the technological artifact interpretation. If, on the other hand, astronomers detect any sign of a deliberate course correction inconsistent with ordinary comet physics, that would represent exactly the kind of hard-to-explain evidence his hypothesis has been waiting for since the very beginning. That tension playing out in real published papers between real scientists, rather than resolved in a single dramatic headline, is exactly what makes this such a compelling story to keep following, regardless of which side eventually turns out to be right. If you want to keep tracking exactly what the next round of data reveals about this interstellar visitor, make sure you like this video and subscribe to the channel, because 3i Atlas still has months left in view before it vanishes from our solar system for good, and we intend to cover every new finding as it comes in.